We are going to look at the graphs of trig functions. It's really the last thing that we have to do in terms of trigonometry. We've looked at the unit circle, kind of started there. The unit circle, take it that away. We started with the unit circle and kind of have that understanding of the unit circle and what all is involved in the unit circle. Then we moved on to evaluating from the unit circle. We looked at evaluating inverse trig functions from the unit circle, of course, being restricted to certain domains, and then output values restricted to certain quadrants as a range for those values. And we kind of understand why we have to restrict the inverse trig functions. Then we moved on to solving trig equations, and when we solve trig equations, we're looking for all the solutions on the unit circle that will solve or be solutions for a particular equation. We looked at different kinds of identities that we can verify, and we learned how to use those identities to simplify trigonometric expressions. So we looked at all of the kind of algebraic part of trigonometry. And what we're going to look at this week is the graphical end of trig. And what do the graphs of sine, cosine, tangent, and then their reciprocal functions look like? Still kind of based on the idea of the unit circle, still having to have that understanding of the unit circle to help us get this graph, but really looking at the graphs of those functions. We know how to evaluate, we know how to solve, and now we're going to really look at how to graph each of those. And for this unit on the graphs of trig functions, we're not going to have a test. Instead, what I'm going to do is give you a project. You're going to be responsible for graphing these, and pay attention in class, take good notes. We're graphing most of them together, so that should be easy. But then what you're going to do on your own is you're going to be looking at the comparison between graphs. So we're going to look at the graphs of sine and cosine, and then you're going to have the responsibility in this project to talk about and discuss some of the similarities and differences between those two graphs. And then, as we go on, same thing for other comparisons between maybe sine and tangent, or sine and cosecant, and so on. And that's what the project is really going to be aimed at, is really your understanding of what these graphs look like and how they are related to each other and where they differ from each other. So again, take good notes and pay attention in class, then that'll help. Now I'm recording this lesson, so I know that there's going to be a lot that are out today and throughout the week. Some people are going to be out for various AP exams, so all the lessons will be recorded. Tomorrow I won't be here, that'll be the day that you'll get your project with the instructions, and then you'll have time in class to start working on that project. So if you do that well, then kind of reduce the amount of time that you have outside of class to work on that project. I would suggest, if you have colored pencils, that you might want to bring those to class tomorrow, because it really helps as you're graphing these different functions. You're going to have to graph multiple functions on the same coordinate plane to kind of look at those comparisons. So if you do that in different colors, then that will help. But you'll have most of the class to work on that tomorrow. Then Wednesday, we'll kind of finish up the graphs of trig functions together, and then you'll have the rest of the week at home to work on the project, so that's ready to submit by the end of the week. Then towards the end of this week, we're going to move into our last unit, which is on logarithms. And I know next week's going to be kind of crazy with AP exams and graduation and so on, so we'll just kind of piecemeal everything together to get through it all, so we finish in time before your exam the following week, because we'll have 3 weeks left. As far as your test on Friday, I'll work on grading that today, and then this take-home assignment will be a grade as well, both those obviously for accuracy. We'll get that in. And then kind of know where you stand, hopefully in the next day or two, with all your grades in. This project can really help you if you use it and do a good job with it. Okay? Before we really get into the idea of what these trig functions look like, and I'm going to forego a class starter today so that we can really dive into the graphs of these trig functions. And I should pull out your flip book. The last tab on that flip book is all of your trig functions. And remember, we kind of changed what the graph looks like a little bit for these. All of our other graphs, we just graphed on the coordinate plane from -10 to 10 for domain range. this one I gave you a little bit different looking graph. We're going to talk about how to label that and why we're using a little bit different looking coordinate plane, although it is the same coordinate plane when we graph these. But before we get into the graphs and what they look like, there's some terminology that we need. There's some terminology that's really specific to the graphs of trig functions, and we need to understand that terminology. In some cases, the terms that we use really mean the same thing as something you're familiar with. We just kind of change the name a little bit. Like, for example, today we're going to talk about a phase shift of a graph, and that's really just a horizontal shift. It's just a different name when we're dealing with trig functions. But there's also other terms that are more specific to the graphs of trig functions, like the period and the amplitude. We're going to talk about those as we go through this. So here is the first term, and maybe one of the most important terms when it comes to graphs of trig functions, and that is the idea that all of these trig functions can be described as periodic. We'll talk about periodic after you write that definition down.
What does t represent in the domain?
T is really just an x value in the domain. So it's kind of like treating it like x. So our definition of a periodic function is that a function is periodic if there is a positive number p such that f of t plus p is equal to f of t for every t in the domain. It's kind of a weird definition. It's very mathy structured when we say that there's a positive number p such that f of t plus p is equal to f of t for every t in the domain. So first off, just think of t as an x value. Okay, so it's just a number in the domain. So it's an x coordinate. In this case, for whatever reason, I label it as a t coordinate, but still think of it like a value in the domain, an x coordinate. What does f of t represent then? What is f of t? What do we call f of x or f of t? It's a function value which is the y, right? So f of t is a y coordinate. Okay? So t is an x coordinate and f of t is a y coordinate. So what this is saying is that for every x, if I add p to that x coordinate, then I'm going to be at the same y coordinate as I was at x. Okay? So f of t is the y coordinate at t. F of t plus p says that if I add p units to the x coordinate, I'm at the same y coordinate. So if you want to put that in words, what that's saying is that for periodic functions, they repeat y coordinates every p units. Okay, so the function repeats y coordinates every p units. That's what all of that definition of periodic means. The function repeats y coordinates every p units. So let's see if we can kind of visualize this. All right. So Kendi, you are at an x-coordinate of -3. All right? And then we'll go -2, -1, 0, 1, 2, and anticipate you're going to be an x-coordinate of 3. All right? So Kendi, I'm going to tell you that as an x-coordinate of -3, your y-coordinate is 4. So hold up the 4. All right. So there's Kendi. She's 4. All right? All right, you are at you're at an x-coordinate of -2, but your y-coordinate is -7. No, -5. So hold up, -5. Negative. There you go. All right. Liana, what is your x-coordinate? -1. All right, and you are the y-coordinate of 0. So hold up 0. All right. So you're at an x-coordinate of 0. Your y-coordinate is 4. All right. Now you're an x-coordinate of, and so your y-coordinate is -5. All right. You're at 2, and your y-coordinate is 0. All right. And then Evan, you're 3, and your y-coordinate is 4. All right. So 4. All right. So everybody's holding up their y-coordinate, right? And what I want you to notice is we started. Kendi has a y-coordinate of 4. Who else has a y-coordinate of 4? Lindsay does. How many x-coordinates does it take for me to get to Lindsay? 3. So if I add 3, 1, 2, 3, I'm at the same y-coordinate. What happens if I add 3 again? 1, 2, at the same y-coordinate. All right? So every 3 units, we're at 4. Let's see if that's true of all of our x-coordinates. All right? At this x-coordinate of -2, we're at -5. If I add 3, 1, 2, 3, am I at the same y-coordinate? Yep. All right. What about this one at -1? Down is -1. She has a y-coordinate of 0. If I add 3, 1, 2, 3, I'm at an x-coordinate of 2, not 0. So no matter what x-coordinate I start with, if I add 3 units to it, I'm going to be at the same y-coordinate. That's what it means to be periodic. All right. I don't have to hold up your y-coordinates. All right. So that's the idea of periodic, is that it's repeating y values at regular intervals. So, if that regular interval is 3, every 3 units, no matter what x-coordinate I start at, every 3 units, I'm at the same y-coordinate. So if f of t is my y-coordinate, when I add 3, in this case, which would be p, to the x-coordinate, I'm going to get the same y-coordinate again. And it happens over and over and over again. Okay? When Kendi was at an x-coordinate of -3 with a y-coordinate of 4, when I added 3, I got to an x-coordinate of 0. I was at the same y-coordinate. When I added 3, I was at a y-coordinate of 3. I'm the same y-coordinate. What would the y-coordinate be at 6? 4 again. What would the y-coordinate be at 9? 4 and at 12. And at -6. All right? And what would be the y-coordinate at... All right, what would the y-coordinate be at +13? It'd be at -5. Why? Because at -2, it's -5, which means that if I add 3 to that, 1, it would be at -5. At 4, it would be at -5. At 7, it would be at -5. At 10, it would be at -5. And then at 13, it's going to be at -5 again. Okay? Every 3 units, it's going to be at the same y-coordinate as the x-coordinate I started at. Okay? What would be the y-coordinate at 36? 4. Why 4? Hello. Check Lindsay. She's 0, right? So 36 is divisible by 3. It's a multiple of 3. So that would mean that at 0, 4. Remember anything? So at 3, 6, 9, 12, 15, 18, 21, 24, 27, 30, 33, 36, we're going to get all of those values are going to be the same y-coordinate of 4. Okay? That's what we mean by periodic. Okay? Whatever that number is, then that we repeat at regular intervals, that's known as the period of the function. Okay? And it's the same for every x-coordinate. It's not like At 0, we'll add 3, but at 1, let's add 5. No, that can't do it that way. It's got to be the same repetition over and over and over again. Have you come across any functions before that repeat y coordinates at regular intervals? Potentially, right, as long as it's horizontal. Okay? It's going to repeat the same y coordinates at regular intervals. Okay? So horizontal lines would do that, but not lines with a slope because their y coordinates are changing. Some people think, oh, the step function, right, the greatest integer function. But is it repeating the same y coordinates? No, the steps look the same, but the y coordinates are not the same. They're getting bigger or smaller. Absolute value, is it repeating the same exact y coordinates at regular intervals? No. Now, if that absolute value looked like this forever, then yes, it would be periodic. But absolute value just goes like that, up and up and up, right? Okay? So no, we haven't come across any function that's periodic. The only functions that are periodic are your trig functions. Okay? So they're going to be examples, unless it's just some random function that's not one of our parent functions. But of all our parent functions, only the trig functions are periodic. Okay? And one repetition is known as a cycle, one cycle of the graph. So, you know, we could draw examples of periodic functions that are not trig functions. They're just not any of our special functions that we're familiar with, or our parent functions. But, you know, ideally, like if you've seen those heart monitors in the hospital, I mean, ideally, that's periodic. If it's not periodic, then you got a problem, right? But, you know, those heart monitors look something like, I don't know, something like this, maybe, where, you know, you've reached that systolic and then diastolic, whatever. So that would be an example, but you know, a periodic function might look something like this. You see how it's repeating y values, same maximums, same minimums all the way throughout. And if you wanted to identify one cycle, then you could kind of start anywhere you wanted. Like maybe you say, I'm going to start here. Then one cycle would go all along here to right there. Because what happens at that point? Yeah, a new cycle starts. So it starts repeating itself at that point. And we have this new cycle here. Green. And then the next one is starting here. And you know, the previous one is ending here. And so on. So it goes like that. You know. So we just have these regular repetitions throughout, and that's one cycle of this periodic function. And however long it takes for it to start, like for example, you know, if this happens to be where 0 is, and this happens to be where 10 is, then in that case, the period of that function would be 10 units. Because it took 10 units for it to start repeating itself. What would this x coordinate be? 20. Okay, good. And I can't go all the way back here, but -10 would be somewhere over here, you know. So that's the idea of a periodic function. And like I said, all of our trig functions are periodic. And the reason why all of our trig functions are periodic is if we think about the unit circle, what happens to the values on this unit circle after we've made one complete revolution around the unit circle? They repeat themselves, right? And remember, we can go around the unit circle as many times as we want, or we can go in a negative direction around the unit circle as many times as we want. But every time that we go around the unit circle, we're repeating values. We're going to end up repeating the range for our sine and cosine and tangent functions. So that's why we're going to have these multiple cycles of our graph. Okay? So let's go to our flip book. We're going to, I used to have this app that it said something like unwrapping the graph of sine and cosine And all that means is that what it showed you was that as you went around the unit circle, it kind of took this circle and it unwrapped it and then formed it into the graph of sine and cosine. But we're going to kind of see how that happens on our own. So let's graph the graph of sine of x. So in your flip book, this could be that first graph. We have y equals or f of x equals the sine of x. Now, we got to label our x-axis first because, the ones I've given to you previously were -10 to 10, but this one doesn't have any labels on the x-axis. The graph that I've given you, I think, let's see, has 8 little marks on each side of the x-axis. And we'll come back and deal with the y-axis in just a second. But what we're going to do is instead of using values, our natural numbers like 1, 2, 3, or integers, really 1, 2, 3, 4, 5, and -1, -1, -2, -3, -4, we're going to instead use label our x-axis in terms of pi. Because as we go around the unit circle, all of the angles on the unit circle are in terms of pi, right? So if we wanted to make one complete cycle all the way around the unit circle, what's going to be the biggest angle that we're going to come across? 2 pi. So we'll call this 2 pi. Now, does the graph keep going? Yeah. Because we can continue to make cycles around the unit circle as many times as we want. So if I made another cycle, then I'd be, maybe over here at 4 pi. And then at 6 pi, and so on and so forth. In fact, on the negative side of the x-axis, this would be -2 pi. Now, remember, this still is a coordinate plane. So I could still kind of lay that coordinate plane on top of this. 2 pi is what, about 6.28? So somewhere around here is 6. Somewhere around here is 3, and so on. But we're just labeling this in terms of pi just to make it a little bit easier to graph. But it still translates to a coordinate plane. Okay, so kind of keep that in mind as we're going through this. This isn't a different coordinate plane than what we're used to. We're just labeling it a little bit differently. If this is 2 pi, what would be halfway between 0 and 2 pi? This is pi. And halfway between 0 and pi is, and halfway between 0 and pi over 2 is pi over 4, right? Half of pi over 2 would be pi over 4. So 1/2 times pi over 2 is pi over 4. What's halfway between pi over 2 and pi? Is it 3 pi over 4? Halfway between pi and 2 pi is 3 pi over 2. Halfway between pi and 3 over 2, halfway between 1 and 1.5 is 1.25, which would be 5 pi over 4. And this one would be 7 pi over 4. When you get to this project, you're going to have to graph some of these functions again on the actual project. If you don't label your x-axis, you won't get full credit. And you have to label your x-axis when you're graphing anything, right? You statisticians. Halfway between 0 and -2 pi would be -pi, and really all of this is just labeled as negative in reverse. Now on our y-axis, again, I have some tick marks on there, but when I'm graphing sine, what do you think is going to be your maximum minimum values for your y-axis? Yeah, 1 and negative 1, right? That's our output values for sine of x. And then what we're going to do to graph this is when we look at this equation, y equals the sine of x, x is our input. And for sine of x, we put angles into that function. We take the sine of pi over 2, or the sine of 3 pi over 2, or the sine of 7 pi over 4, or whatever. So the x, our domain, just as we've labeled along the x-axis, are going to be our angles. Our y is going to be our output value. And from the unit circle, where do we get our sine values? Like if I say the sine of 3 pi over 4, the y coordinate, right? So our output value is going to be all of the y coordinates of each of these angles along the unit circle. Okay? So our input would be pi over 4, which is 45 degrees. Our output is the sine value there, which is the square root of 2 over 2. So let's do that for all of these angles along the x-axis. At an angle of 0, what is the output value, the sine value at 0? You want to have your unit circle out in front of you, that might help. So what's the sine value at 0? 0. Okay. What is your sine value at pi over 4? Square root of 2 over 2. Put that in your calculator so we can get a decimal value that we can actually use. 0.707. So at pi over 4, the sine value is 0.707. So that's going to be somewhere around in here. What's the sine value at pi over 2? 1. What's the sine value at 3 pi over 4? Positive square root of 2 over 2, so that's going to be 0.707 again. What's the sine value at pi? 0. Right? You see how we're just going along the unit circle and pulling the y coordinates at each of those angles? We're plotting those y coordinates, and then now our graph is going to start to take shape. What's the sine value at 5 pi over 4? Negative square root of 2 over 2. At 3 pi over 2, and negative 1 at 7 pi over 4, negative square root of 2 over 2, and at 2 pi, 0. So here's what the graph of sine is going to look like based on these points. Now, negative pi over 4 is coterminal with 7 pi over 4. If I were to subtract 2 pi, then I'm at negative pi over 4. So it's going to have the same y coordinate as we have at 7 pi over 4. And then negative pi over 2 is coterminal with 3 pi over 2. So it's going to have the same y coordinate as we have at 3 pi over 2. And so on. And so here is another cycle of the graph of the sine of x. And then that graph repeats itself over and over and over again. What is the period for the graph of sine? 2 pi, good, because that's how long it takes for it to start repeating itself over again, right? 2 pi units, every 2 pi units is going to be repeating itself. Okay. Everybody good? All right, why don't you try to graph cosine? I'll give you a few minutes to do that. I think a lot of you are finishing up your graph of cosine. What you're going to do for your project is you're going to do some comparison between graphs. So, you graph sine together. You should have gotten a graph for cosine that looks something like this. I think that's right. That look about right? So it's pretty obvious that there are some similarities and a few differences between these two graphs. I'm going to want you to write some pretty specific mathematical stuff to do the comparison between these two graphs. But pretty obviously, these two graphs have the same shape, right? It's just that there's maybe some kind of shift between these two graphs, but they look the same. I mean, to me, they both look like you're driving down the interstate, you roll down the window, and you stick your hand outside the window, and your hand does this, right? And that's the graph of sine and cosine. That's what it looks like, okay? So there's definitely some similarities and differences. You're going to talk about those similarities and differences in the project. So you're going to tell me in paragraph form with complete sentences, which is like a capital letter at the beginning and a period at the end of each statement. You're going to write in complete sentences some comparisons, some similarities and differences between these two graphs. Okay? And there's a lot. I mean, you can talk about their period. What can you tell me about the period of each of these graphs? They're both 2 pi, right? In a second, once I introduce the concept of the amplitude, then you're going to be able to see or say both of these have the same amplitude of 1. But there's some differences. Like, for example, the places where they cross the x-axis are different. And there's a reason for that, right? In fact, you could even talk about how when one crosses the x-axis, it looks like the other is at a maximum or a minimum value. There would be a good discussion to have about, sine and cosine and some of their differences. You can even relate it back to the unit circle and tell me why they have different values between, where one is at a 0, the other one's at a maximum or minimum. So those are the things you're going to talk about as you graph these. Okay? Everybody good with sine and cosine? All right, then let's, on your flip book, skip one. That will be tangent, but we're going to come back to that. And then let's graph underneath the crease cosecant. And I'm going to leave the graph of sine up because there's definitely going to be a connection between the graphs of sine and cosecant. Why? They're reciprocals of each other, not the inverse, they're reciprocals of each other. Okay? And we know that, so wherever sine is at a particular value, sorry, my voice is giving out. Cosecant is at the reciprocal of that value. Okay? So I'm going to leave the graph of sine up here for reference, but you're going to be making, on your flip book, the graph of cosecant. So for cosecant, I'll give you a second to go ahead and label your x-axis. We'll label it the exact same way. So for the graph of cosecant, let's start with the places where sine is 0. Okay? I'm going to graph cosecant up here in blue. Just so you have sine of x is black. So you can make some comparisons here. And then this will be y equals cosecant will be in blue. So since we know that cosecant is the reciprocal of sine, let's really start with the places where sine is 1 or negative 1. Because those are going to be easy values to find the reciprocal of. What's the reciprocal of 1? 1. What's the reciprocal of negative 1? Negative 1. So at the places where sine is 1, cosecant is still going to be 1. And where sine is negative 1, cosecant is still going to be negative 1. What about the places where where sine is 0? What's the reciprocal of 0? Undefined, right? Because if sine is 0, then cosecant is going to be 1 over 0. So reach back. We talked about this before. What do we have graphically when we get a 0 in a denominator? Either a whole or an asymptote. Okay? When does a whole occur? Say again? Not necessarily, because it could be either a whole or an asymptote when an x coordinate produces an undefined value. But what has to happen for there to be a hole in the graph? You remember? And we factored the numerator and denominator. And what happened in the case of a hole after we factored? Something canceled, right? There's a common factor in the numerator and denominator. That's when a hole occurs. Well, in this case, I'm taking 0. I'm doing the reciprocal of it. I'm getting 1 over 0. There's nothing that's going to cancel. If it was going to cancel, then I would have gotten 0 over 0. That's not happening here. I'm just, the reciprocal of sine is 1 over sine. And then when I plug in 0 for x, I get 1 over 0. So nothing's canceling. So that means it's not going to be a hole. At the places where sine has a value of 0, cosecant is going to have an asymptote. Specifically, what kind of asymptote? A vertical one. So the places where sine is 0, cosecant has a vertical asymptote. So we've labeled our vertical asymptotes. We also have the points where sine was 1 or negative 1. Cosecant's going to be the same value. So then it's just a matter of kind of determining what's happening in between these vertical asymptotes. So let's say that we take the value here at pi over 4, which was square root of 2 over 2, and we do the reciprocal of that. What is 2 divided by the square root of 2? All right, so here at pi over 4, where sine had a value of square root of 2 over 2, cosecant's going to have a value of 2 over the square root of 2, which is about 1.414. Same thing here at 3 pi over 4. At 5 pi over 4 and 7 pi over 4, it's negative, so it'll become negative 1.414. Same thing at negative pi over 4 and negative 3 pi over 4. And here at negative 5 pi over 4 and negative 7 pi over 4 become positive 1.414. Now, if I wanted to be more exact, I could choose more angles. I mean, we didn't use pi over 6, but I could have. And the value of pi over 6, the sine value of pi over 6 is a half. which pi over 6, that makes sense. That's about half. If I flip that over, then I would be at 2. Same thing over here at 5 pi over 6. It'd be at 2. So, what ends up happening is the graph looks something like this. And then down here, it's like this. Which makes sense. I mean, we know that a graph is not going to cross a vertical asymptote, that it's going to, that an asymptote is a lot of the graph approaches, so that as it gets closer and closer to those vertical asymptotes, the graph's just going to kind of run right along those vertical asymptotes. So what we have in blue would be the graph of cosecant. And I just used sine as a reference. So here's what the graph of cosecant would look like. Okay, you try graphing secant. Okay, so you should have the graph of secant up, and it's going to like cosine in comparison to sine. Secant is going to look very similar to the graph of cosecant, but it's obviously going to have been shifted some because we base the graph of secant off of cosine, which was shifted slightly from the graph of sine. All right, let's start filling in some of the descriptors that we have there on the side of each of those graphs. We start with sine. We know the function is y equals the sine of x. Tell me about its domain. It's the domain for sine. Yep, negative infinity and positive infinity. The domain for sine is all real numbers. Now, if we were going to, we would have to restrict it to be between negative pi over 2 and positive pi over 2 if we were going to graph inverse sine. We talked about that in the last unit. But the actual parent function for sine of x has a domain of all real numbers. And what is its range? Negative 1 to 1 with brackets. Does the graph of sine have any symmetry? What kinds of symmetry are there? There's y-axis symmetry, x-axis symmetry, and origin symmetry. Of course, no x-axis symmetry if we're dealing with functions. And this has, which one? Don't doubt yourself, you're right. Origin symmetry, right? This has origin symmetry. If you took the part of the graph that was in the first quadrant and you reflected it over the x-axis and over the y-axis, then you would get that same part down to the third quadrant. So it has origin symmetry. Since it has origin symmetry, how would we label it? Odd. Is it a one-to-one function? No, that's why we have to restrict its domain if we want to graph inverse sine. The parent function is not a one-to-one because it doesn't pass the horizontal line test. Does it have any asymptotes? No. This one's a little different. Tell me about the intercepts of the graph of sine. Zero, pi, 2 pi, negative 2 pi. And we could keep going. 3 pi, 4 pi, 5 pi, negative 3 pi, negative 4 pi, negative 5 pi. Really at all the intervals of pi, right? So previously all of our graphs, there was a single x coordinate or a couple x coordinates. But this one we have an infinite number. So here's how we can represent that. We can say that the x-intercepts occur at all the x's such that x equals plus or minus pi n. So those would be all of our x-intercepts, all the x's such that x is equal to either positive or negative pi n, where n is just some natural number. So n could be 0, really natural number then I guess, whole number. N is 0, could be 1, 2, 3, 4, 5, all the intervals of pi. Okay. Does it have a y-intercept? Yeah, where? At 0, the origin. Does it have a minimum value? -1. Okay, and that occurs at multiple places. The smallest y coordinate is -1. And what's its maximum? 1. And in terms of end behavior is what's happening as the graph approaches infinity or negative infinity. And the graph of sine, as we get larger and larger, just keeps bouncing up and down from -1 down to, up to 1, down to -1, up to. Does it ever appear like it's approaching anything? No. So it really doesn't have any end behavior. Okay, nothing that we can define. So there is no end behavior. Let's run through cosine real quick because this should be pretty easy. Domain is the same. Range is the same. Any symmetry? Y-axis symmetry. If you fold it over the y-axis, it's going to look the same.
How do you not get that for without cheats?
If I take this piece, fold it over the y-axis, I'm going to get this piece. I take this, fold it over the y-axis, I'm going to get this. Okay, but for this one, I take this piece, I have to fold it over the x and the y-axis. If it's y-axis symmetry, then that makes it even. Is it 1-to-1? No, that's why if we want to graph inverse cosine, we have to restrict it to be between 0 and pi. But the parent function is not 1-to-1. Does not have any asymptotes. Its x-intercepts occur where? Pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, negative pi over 2. All the pi over 2's, right? So in cosine, we'll still do all the x's such that x equals plus or minus pi over 2 n. So that would give us 1 pi over 2. Well, I can't really do that. Hold on, that's not right. Just kidding. It's at pi over 2 plus or minus pi n. Sorry about that. Because what that'll do now is it'll start us at pi over 2, and if I add pi, then I'm at 3 pi over 2. If I add pi again, I'm at 5 pi over 2. Or if I were to subtract pi, I'd be at negative pi over 2, negative 3 pi over 2, and so on. Any y-intercept at 1, minimum, maximum, good, and no end behavior. All right, let's get down to cosecant. All right, cosecant, a little different. Is its domain all real numbers? No, why not? So we have asymptotes. So where do we have asymptotes? How does that compare to sine? All the intercepts, right? And all the intercepts of sine, cosecant is undefined. So for cosecant, here's what we can do. Our domain is going to be all the x's such that x does not equal one of the intercepts for sine. So all the places where sine had an intercept, now we have to exclude those from the domain of cosecant, because that's where our vertical asymptotes lie. What about its range?
Greater than 1 or greater than less than just negative.
All right, so its range would be from negative infinity to negative 1 in union with 1 to infinity. So really, we're leaving out that part between negative 1 and 1. Any symmetry? Origin, just like sine, has the same symmetry, which makes it odd. It's not 1 to 1. It does have asymptotes. Where are its asymptotes? Right, all the x's such that x is equal to plus or minus pi at the intercepts of sine. Any x-intercepts? Nope. Y-intercepts? Nope. Have a maximum value? Nope. Have a minimum value? Nope. Have any behavior? Nope. All right, fill in secant real quick. All right, so for secant, what is the domain?
X, if that X cannot equal higher than 2 plus or minus pi.
Good. So at all the places where cosine had x-intercepts, now secant is undefined, so x cannot equal those values, but it can equal everything else. What's the range for secant? Same thing as it was for cosecant. Any symmetry? Y-axis, which makes it even. Is it 1 to 1? No. Does it have asymptotes? Yeah, and all the x's such that x does equal pi over 2 plus or minus pi n. All the x-intercepts of cosine become the asymptotes of secant. And does it have an x-intercept? No. Does it have a y-intercept? You have 1. Does it have a minimum, maximum, and behavior? All right, so we got all those filled in. All right, good. Let's talk a little bit about some more specific terminology in relation to sine and cosine. And again, this will help you with that project as you discuss some of the similarities and differences between these different graphs. We've already said that the period for sine and cosine apparent functions is 2 pi. We know that. Another term in relation to the graphs of sine and cosine would be the amplitude. And by definition, the amplitude, and you probably, if you've taken physics, you probably have talked about sound waves or light waves, and probably referenced difference, the amplitude of those waves. But the amplitude of a sine or a cosine function is half the difference between the largest and smallest values of the function. Half the difference between the largest and the smallest values of the function. So for sine and cosine, what's the biggest value? 1. What's the smallest value? -1. How far apart are those two values? 2 units, and half of 2 is 1. So the amplitude for sine and cosine is 1. And that makes sense when you look at the graph because it goes up to 1 and down to -1. Now we can change that. Well, let's say a function has an amplitude of 1, but if it has a vertical shift, then it won't go from -1 to 1 anymore. If it has a vertical shift of 5 units, that means everything's been shifted up 5. So now the biggest value would be 6, the smallest value would be 4, but the amplitude is still 1 because it's half the difference from the biggest to the smallest value. Okay? But for the parent function for sine and cosine, the amplitude would be 1. And so all of our sine and cosine curves, without any kind of shift, have this form. Y equals a sine of bx. So our parent functions are y equals sine of x and y equals cosine of x. But, just as we've done with all of our parent functions, we can shift them, move them, stretch them and shrink them. And, the way that we can really stretch vertically and horizontally is by affecting the values of a and b. And in this form, and this is what you're going to need to add to the notes, a is the amplitude. So when it's written in the form y equals a sine of bx, a is the amplitude. And then the period is determined by doing 2 pi over b. The period is 2 pi over b. That's really important because now when we look at these these graphs, these functions, when they're not written as a parent function, we want to be able to identify the amplitude and the period. Those are significant components to the graphs of sine and cosine. And we can find those from the graph by a being the amplitude and 2 pi over b being the period. And another thing that b stands for, and you might want to write this as well, is that b represents the number of cycles between 0 and 2 pi. B is the number of cycles between 0 and 2 pi. So, kind of reason this out, if b is 2, then how many cycles do we have between 0 and 2 pi? 2, which means the length of each cycle would be what? Pi, right? Because if I'm normally 0 to 2 pi, but now I've got to squeeze 2 in there, then now they're each going to have a length of pi units, which I determined by saying 2 pi over b, or 2 pi over 2, which reduces to pi. Okay? So, let's hold off on that. Let's say that I want you to write the equation and I tell you that I want it to be a sine function with amplitude of 4 and period of pi over 2. So we want a sine function that has an amplitude of 4 and a period of pi over 2. So that's going to be y equals, and I'm going to fill in a and b in this sine function. A is easy. What would that be? 4, because that number in front of sine is the amplitude. just like when we got a number in front of the function and we multiply the y coordinates by that number, now we're going to multiply the y coordinates, which are 1 and negative 1, by 4, which will take me from 4 to negative 4. And then b, remember, how do we find the period? 2 pi over b. Well, that's equal to pi over 2. So what would b have to be? So this function would be 4 sine of 4x. All right, what about this one? I want a cosine function reflected over the x-axis with an amplitude of 5 and a period of 6 pi. Let's see. Cosine function that's reflected over the x-axis has an amplitude of 5 and a period of 6 pi. So I know it's going to be in this form. It's a cosine function. If the amplitude is 5, then I'm going to put a 5 out front. How do you reflect something over the x-axis? Negative where?
Up front.
Out front. Good. So it's going to be negative 5 cosine of bx. And we've got to figure out what b is. Well, our period we find by doing 2 pi over b. In this case, the period is 6 pi. So I'm going to cross multiply, and I'm going to get 2 pi equals 6b pi. And I'll divide by 6 pi. And what do you get for b? 1/3. So it's negative 5 cosine of 1/3 x. Now let's try one more. I want you to write the equation for this one. Well, first off, you're going to have to determine, are we talking about a sine function or a cosine function? Sine what? Goes through the origin. Good. Could it be a cosine function? It could be, right? It would just be that there would have been some kind of horizontal shift to make it go through the origin, because typically cosine goes through 1 or negative 1, right? It goes through the amplitude, where sine goes to the origin. Now, we could shift that horizontally, but it's just a lot easier to call this a sine function. What's the amplitude of this sine function? 4, yeah. So the amplitude is 4 because the biggest y value is 4 and the smallest y value is negative 4. So the amplitude is half the difference between the biggest and the smallest value. So from 4 to negative 4 is 8 units, and half of that is 4. And then what would b be? 3y. All right, good. There's 1, 2, 3 cycles between 0 and 2 pi, and so therefore that's going to be y equals 4 sine 3x. Okay? So tomorrow, what you're going to do is the sub will hand out your project. You can be working on that project. You'll also, I think, have a class starter that you'll work on. That'll be your assignment tomorrow in class. And then Wednesday, what we'll do is we'll look at horizontal and vertical shifts and tangent and cotangent. And then you should be able to finish off your project by the end of this week.